Hello. This presentation covers the basics of conventional and organic fertilizers. This module should be viewed as a starting point in your education regarding fertilizers, in that the subject is very broad and cannot be given in enough detail for mastery of the subject in a 40 to 50 minute presentation. This presentation was put together by Shelby Henning and Jeff Kindhart and is narrated by Mike Kruger up at the St. Charles Horticulture Research Center. Let's first start with the basic definition of what fertilizer is. Fertilizer is any organic or inorganic material of natural or synthetic origin that is added to a soil to supply one or more plant nutrients essential to the growth of plants. Generally, this definition is broken down into two or more categories of fertilizer, these being organic or conventional, inorganic or synthetic. One can debate the definition, but for most purposes, conventional, synthetic, inorganic fertilizers are manufactured. Organic fertilizers, on the other hand, are derived from naturally occurring mineral deposits or organic materials. And an example of a conventional inorganic synthetic fertilizer would be urea. For organic, a naturally occurring fertilizer would be something such as manure or animal waste. A common question is whether a grower requires the use of fertilizer. In many cases, plants will grow without application of exogenous fertilizer. There are documented cases where fertilizer addition did not result in increased yields. If the crop being grown demands more nutrients than the soil can supply, fertilizer addition is necessary and beneficial to yields. The question now becomes, how much fertilizer do I need? The law of diminishing returns is applied here. You should only add enough fertilizer to optimize your yields. Any amount below optimal reduces yield, and any amount above wastes resources and the potential yields as well. One approach a grower can use is on-farm fertility trials. These trials can help a grower determine near optimal rates for fertilizer addition tailored to their specific farm. There is some debate regarding what nutrients are necessary for crop growth and development. Those nutrients that are agreed upon as necessary are termed essential. That is, the element is required for plant to complete its life cycle. No other element can substitute, and the element must be directly involved in the nutrition of the plant. Justus von Liebig popularized the law of the minimum concerning essential nutrients, stating that the plant growth is controlled not by the total amount of resources available, but by the scarcest resource. Thus, one must manage fertility in a balanced approach in order to maximize yields. Basically, the law of the minimum is saying that you could have, say, all the nitrogen and phosphorus in the world in that soil, but if potassium is in limited supply, that plant is not going to grow to optimum yields unless potassium is raised to the necessary amount for the plant. Essential nutrients include the structural nutrients of carbon, hydrogen, and oxygen, and are not derived from soil or fertilizer. Macronutrients are nitrogen, phosphorus, potassium, calcium, magnesium, and sulfur. Nitrogen, phosphorus, and potassium are primary nutrients, and calcium, magnesium, and sulfur are the secondary nutrients. Both primary and secondary nutrients are derived from soil or fertilizer. Other essential nutrients are micronutrients. Micronutrients are required by the plant in very small amounts, generally less than 50 milligrams of nutrients per kilogram in the plant. There is some scientific debate as to the essentiality of some proposed micronutrients. Great care must be taken with micronutrients applications, as toxicity can occur when these micronutrients are applied in excess. When determining if a micronutrient application is in order, plant tissue testing should be undertaken to determine the proper course of action. Generally, most fertilizer manufacturers are concerned with the macronutrients. Most containers of fertilizer will have a guaranteed analysis or grade of the nutrient content in the container. What's actually printed on the container varies from state to state, but generally includes the name brand, guaranteed analysis, potential acidity, manufacturer's name, and the address, and the weight of the fertilizer in the container. Fertilizers are further categorized as complete, meaning the fertilizer contains all three macronutrients, nitrogen, phosphorus, and potassium, or incomplete, meaning one or more of those nutrients is missing. For instance, take a long look at this hypothetical container of fertilizer. Not only does the bag in question have a brand name and place of manufacture listed, the fertilizer grade is also included. Moving on to specific nutrients, let's take some time to discuss one of the most important nutrients required by plants, nitrogen. Crops differ in their ability to take up nitrogen from the soil solution. The efficiency of the process differs due to soil nitrogen supplying capacity, weather conditions, plant population, plant age, and the specific crop. Not all fertilizer that is applied is taken up by the crop. Frequent estimates of crop uptake are 30 to 50% of the applied nitrogen. Even with high nitrogen dosage rates, the soil often supplies the majority of the crop nitrogen. The amount of nitrogen labeled on a nitrogen fertilizer is a percentage of the weight of the fertilizer in question. Simply put, a fertilizer that is 46% nitrogen contains 0.46 pounds of nitrogen per pound of fertilizer. The nitrogen in the bag is often further delineated into water-insoluble nitrogen and water-soluble nitrogen. Water-insoluble nitrogen is slowly available, while water-soluble nitrogen is quickly available to the crop being grown. So as another example, a fertilizer that is labeled 50% nitrogen in a 100 pound bag of fertilizer is going to be 50 pounds of nitrogen. There is a perception that synthetic nitrogen fertilizer can injure plants easily. Frequently, this is a result of improperly calibrated equipment and less than optimal post-application handling. Some synthetic nitrogen fertilizers are much more prone to injury than others. The reason this phenomenon occurs relates to a fertilizer's salt index. A good discussion of salt index can be accessed by following the hyperlink on this slide of the presentation. As you can see, specialty crop producers are the most at risk compared to other crops. Take time to understand the fertilizer you are using prior to placing it in the field. Anhydrous ammonia is a popular nitrogen fertilizer for row crops such as field corn. The main advantage is its very high in nitrogen content, around 82%. But there are several drawbacks to anhydrous ammonia as a fertilizer. Anhydrous ammonia must be stored and applied under pressure. It is very corrosive and hazardous to human health. Anhydrous ammonia must be incorporated immediately into the soil or losses of nitrogen can be excessive. It greatly affects soil when it is applied and is often stolen for use in illicit drug synthesis. Normally, anhydrous ammonia is not used in the cultivation of specialty crops. Aqua ammonia is a low pressure solution of ammonia in water containing 20 to 25% nitrogen. It must be incorporated into the soil or volatile losses of fertilizer nitrogen can be great. Like anhydrous ammonia, aqua ammonia is not frequently used for vegetable crop culture. Urea ammonium nitrate is non-pressure solution of ammonium nitrate, urea, and water. There are two common grades, 2800 and 3200. Salt crystals will form in each solution if they are not allowed to get cold enough. Urea ammonium nitrate are much safer than anhydrous ammonia or aqua ammonia. Urea is one of the most popular synthetic nitrogen fertilizers for specialty crop culture. It is relatively high in nitrogen at 46% and poses little safety risk to those that use it. Proper post-application handling is essential so that nitrogen losses can be minimized. The easiest way to mitigate losses of applied urea is to incorporate the granules either mechanically or by watering in. Ammonium nitrate is a popular nitrogen fertilizer, more so in Europe than the US. It has a lower nitrogen content than urea, and half the applied nitrogen is in the nitrate form, which can lead to leaching losses. It can be used in the manufacture of explosives, which makes it obtaining the material difficult. The compound is well known to form hard cakes upon storage and can make it difficult to apply. Ammonium sulfate is another popular synthetic nitrogen fertilizer. Advantages of ammonium sulfate is that incorporation is not necessary to mitigate nitrogen losses, and due to its acidic nature, nitrification is slowed. Ammonium sulfate also has a benefit in that it provides sulfur, a secondary essential nutrient, as well as nitrogen. Drawbacks to the use of ammonium sulfate are its relatively low nitrogen content and its ability to burn above ground plant parts if it is not washed off by irrigation or precipitation. Potassium nitrate is a popular synthetic nitrogen fertilizer for specialty crop production. It is frequently employed through fertigation to solanaceous crops. Of the many advantages to its use, it also supplies potassium as well as nitrogen. Calcium nitrate is another popular synthetic nitrogen source for specialty crop production. Not only does the material supply nitrogen, but also calcium to plants. One drawback to use calcium nitrate is relatively low nitrogen content. There are several hybrid sources of nitrogen and phosphorus used to fertilize crops. The three common materials are monoammonium phosphate, which is 11,520, diammonium phosphate, which is 18,460, and ammonium polyphosphate, which is 10,340. A drawback to using the materials is that if they are used as the sole source of nitrogen, it is very likely to result in the overapplication of phosphorus. Over the past 30 years or so, advances have been made in controlling the release of nitrogen from completely water-soluble synthetic nitrogen fertilizers. The technology generally relies on coating a urea granule with a substance that retards the dissolution of urea into the soil system. Advantages to these products is that they are not likely to cause burn. Nitrogen losses from the system are reduced or eliminated, and the plant growth is more uniform. Disadvantages to these materials is that they can be expensive, not work on cold soil until later in the season, and plant response may be very slow. Another class of synthetic nitrogen fertilizers are those termed stabilized. Again, this technology is applicable to ammonia-based fertilizers such as urea. Stabilizers are materials that inhibit transformations of the applied fertilizer that may lead to nitrogen losses. Do not confuse these materials with slow-release fertilizers. Again, specialty fertilizers can be far more expensive than the materials they are manufactured from. Organic nitrogen fertilizers were a major agricultural source of nitrogen for farming prior to 1920. There are a huge variety of materials that can be classified as organic nitrogen fertilizers. One drawback is a relatively low nitrogen content. These materials are generally safe and do not cause rapid flushes of plant growth. These materials can be a cause for environmental concern regarding their use and should not be regarded as possessing no negative qualities. The list of approved organic nitrogen fertilizers in the U.S. is quite large and as precludes a detailed discussion of the materials in this presentation. An exhaustive list of approved materials can be accessed using the hyperlink on this slide. Animal manure has long been used as a source of organic nitrogen fertilizer. Manure is generally of local importance due to the costs associated with shipping the material. A heavy reliance on manure as a sole source of nitrogen for an operation can lead to phosphorus accumulation in the soil. Frequent soil tests should be employed at sites where animal manure is used to ensure that phosphorus is not being over-applied. Sewage sludge is another organic nitrogen fertilizer of local importance. Sewage sludge is derived from human waste and processed to reduce heavy metal contamination and to improve handling characteristics. There are two classes of sewage sludge. Class A has no restrictions on its use, while Class B is restricted in where it can be applied. Bear in mind that both classes may contain radioactive or pharmaceutical waste derived from materials of origin. Sewage sludge tends to have more variable nitrogen content, which dictates how much should be applied to meet a producer's nitrogen requirements. As with manure, over-application of phosphorus could be a concern of those using sludge as a sole source of nitrogen for their operation. Cover crops are becoming more popular and they can provide some nitrogen to a growing operation. Keep in mind that non-leguminous plants do not supply much nitrogen, but are useful in increasing soil organic matter and reducing erosion. There are many options. A detailed report is available via the hyperlink on this slide of the presentation. Animal byproducts are products of the slaughterhouse industry. These organic nitrogen fertilizers are manufactured from a wide variety of materials such as blood, bones, feathers, and fish meal. Most of these products tend to have a very offensive odor, are expensive, and are slow-release materials. Mineral forms of organic nitrogen fertilizer are somewhat rare, but examples do exist. Chilean nitrate and bat guano are two examples of organic nitrogen fertilizer that can be mined. Moving on to phosphorus fertilizers. While the number on the fertilizer container indicates the actual amount of nitrogen in the bag as a percentage of weight, the same does not hold true for phosphorus and potassium. The amount of phosphorus in a particular container is actually expressed as phosphorus pentoxide, which is only 44% actual phosphorus. To obtain the actual amount of phosphorus in a fertilizer, the amount of phosphorus pentoxide should be multiplied by 0.44. There are several thoughts as to why this system is accepted. First, the system has been in place for a very long time. There is also some speculation that compared to nitrogen, using the actual concentration of phosphorus and potassium in a bag of fertilizer may lead the purchaser to conclude they are not getting the fair end of the deal. Unlike nitrogen, phosphorus is taken up throughout the life of the plant. The early growing season is the most critical for phosphorus nutrition, as seedlings require phosphorus for root growth, and the root system early in the life of the plant is small. There are several synthetic phosphorus fertilizers. All synthetic phosphorus fertilizers are derived from phosphoric acid. Phosphoric acid has a grade of 0,50 and is manufactured from the mined rock phosphate. Phosphoric acid is of some use in fertigation, but its main use is in the manufacture of other phosphorus fertilizers. One of the oldest manufactured phosphorus fertilizers was single superphosphate, aka ordinary superphosphate, or normal superphosphate. Ordinary superphosphate also supplies sulfur, around 12%, as well as phosphorus, 8.6%, and was a leading phosphorus fertilizer in the U.S. until the advent of triple superphosphate in the 1950s. Triple superphosphate supplies much more phosphorus, around 46%, than single superphosphate. Its high analysis reduces costs and was a leading phosphorus fertilizer in the U.S. in the 1950s and 1960s. Ammonium phosphates are synthetic phosphorus fertilizers that supply nitrogen as well as phosphorus. These include monoammonium phosphate, 11,520, diammonium phosphate, which is 18,460, and ammonium polyphosphate, which is 10,340. Diammonium phosphate is the most common phosphorus fertilizer in the U.S. Ammonium phosphates have several advantages. They are water soluble, supply phosphorus as well as ammonium, and have a high phosphorus content. Coupled with the fact that they can be applied as either a liquid or a solid, they give the producer great flexibility in application. For a reason that is not wholly understood, phosphorus uptake is increased in plants in the presence of ammonium, another benefit of the ammonium phosphates. Again, advantages of monoammonium phosphate include increased nitrogen efficiency, no ammonium volatilization, and no ammonium toxicity. Monoammonium phosphate possesses an extra benefit in that it can be manufactured from a lower grade of rock phosphate than diammonium phosphate. Polyammonium phosphate has advantages in that it is high in phosphorus content, high phosphorus solubility, and good fertilizer use efficiency values except in cool soils. Other synthetic phosphorus fertilizers include nitric and potassium phosphates. Nitric phosphate supplies nitrogen as well as phosphorus and has analysis of 20-20. Only approximately 50% of the phosphorus is water soluble. Nitric phosphate is mainly used in Europe and is best suited for application to acidic soils. Potassium phosphate is available in two grades, 0,5235 and 0,4154. Both grades are mainly used for fertilization of high-value crops such as vegetables. Potassium phosphate possesses a high content of phosphorus and potassium. Its phosphorus content is 100% soluble and is used in sensitive crops such as potatoes and tobacco to supply potassium without chlorine. Again, the cost of potassium phosphate fertilizer can be prohibitive. Animal manure accounts for most organic phosphorus applied to cropland. Phosphorus form and content are dependent on the type of handling and the conditions the manure was stored under prior to application. The general composition of animal manure is approximately 0.5-0.25-0.5 by weight. Again, high levels of manure can increase phosphorus levels in the soil to undesirable levels. Sewage sludge can be utilized as an effective organic phosphorus source. Sewage sludge generally contains 2 to 4% phosphorus on a dry weight basis. Most of the phosphorus is inorganic. Again, high levels of phosphorus in sewage sludge can result in excessive phosphorus soil test levels if attention is not paid. Again, heavy metal accumulation can be a problem if using a lower grade of sludge. Rock phosphate is a mine source of organic phosphorus fertilizer. Unless the soil has a pH less than 6, rock phosphate is of very limited use as an organic phosphorus fertilizer. This is because at a pH range above 6, phosphorus forms a phosphorus precipitate that is not plant available. As with lime, the smaller the granule, the quicker the release of the phosphorus into the system. Synthetic potassium fertilizers are all mined from mineral deposits. Potassium chloride or muriate of potash is the most common potassium fertilizer. There are two fertilizer grades, red containing 60% and white containing 62% potassium. One advantage is that mineral deposits of potassium do not require chemical processing for the use of fertilizer materials, and as such are much less expensive than nitrogen or phosphorus fertilizer. Processed forms of mineral potassium include potassium sulfate, aka sulfate of potash. Potassium sulfate has a fertilizer grade of 0050-17. The 17 would be sulfur. This material is used for fertilizing chlorine-sensitive crops. Potassium nitrate is very popular with specialty crop growers. It not only supplies nitrogen but potassium and has a grade of 13-0-44. Processed mineral forms of potassium include alkaline potassium fertilizers such as potassium carbonate and potassium hydroxide. These materials are good for use on acidic soils, but are expensive. Potassium fertilizers containing sulfur such as potassium thiosulfate and polysulfide are also expensive. These materials are highly soluble and suited for foliar applications and fertigation. Organic potassium fertilizers include animal manure, kelp, and seaweed. Animal manure exhibits a potassium content that is less variable than for nitrogen and phosphorus, and available potassium is generally less than 4 pounds per ton. Kelp and seaweed contain inorganic potassium salts. These salts are water soluble and will leach into the soil to provide a good source of potassium. Some final thoughts to consider is to always conduct a soil sampling on a repeated basis, so as a grower you know what your fertilization goals should be. On-farm trials will help you dial in your fertilization needs, specific for your site. I would like to add that just because a particular material is synthetic or organic does not lend it to automatic justification for its use. Try to keep an open mind. Some materials are cost prohibitive, and the specialty crops business runs by the basic laws of economics.